Okay, so what we have done is reactive extraction. We have looked at basics of extraction. We have looked at extraction equipment. We have looked at reactive extraction, and now we are going to start looking at something called as dissociation extraction. So don't worry too much about the name. What this dissociation extraction is, let's look at the principle first, then we will go to some of the problems and how it can be used for separating different compounds. So the basic principle is that there are weak acids and weak bases. Now compounds are sometimes acidic in nature or basic in nature. So for example, if we take phenol, we talked about this phenol. So this phenol can dissociate as O minus and H plus. But this dissociation constant is very small. So it's a very weak acid, right? And therefore I can react it with a base, but now that base can be in a different phase. So we've seen this kind of reactive extraction. Now what this dissociation extraction we are going to see is that we are going to have two such compounds which are having different acidity or different basicity, and we are going to be able to separate them on the basis of their acidity or basicity. So what we are going to look at first is how do I characterize the acidity and basicity of these compounds. So in your undergraduate course, in your chemistry course, you must have talked about acidity. There are two types of acidity you might have talked about. Bronsted acid, that means it tends to lose a proton. So like phenol, AH, so A would be the phenoxide ion or phenolate ion if you want, right? So it would tendency would be to dissociate into A minus and H plus. Or if you want to talk that in presence of water, it would dissociate that H plus is a proton, so that proton does not really exist. It exists as a H protonated complex if you want, or a protonated or a hydrated or a solvated proton. So you would say that AH reacts with water will give you A minus, and H plus combined with H2O, so that is H3O plus, that is a Bronsted acid. Or it has a tendency to accept lone pair, like for example it reacts with O of water, or ammonia has a lone pair, N has a lone pair. So those are called as Lewis acid. So it will behave, if you take water, it would dissociate, or it would attract a lone pair, and it would become AOH minus and H plus, right? We can think of different examples. You can look at your undergraduate course and undergraduate chemistry books, and you can find these out. Or if you talk about a base, then a base would be, it will dissociate, like for example ammonium hydroxide, NH4OH, it will dissociate into OH minus and NH4 plus ion. So that's a Bronsted base. Or it would react with water and make BH plus and OH minus, a Lewis acid, tendency to accept a proton, because the base has a lone pair, nitrogen lone pair, so it will accept a proton. So that is called as a Lewis base, right? So you remember all that. One of the ways we characterize how much of it dissociates, we characterize by writing an equilibrium constant. Do you recall all of that? So if not, at this point of time, you can stop, you can look at the some of your undergraduate chemistry textbooks if you like. So if I say that this acid dissociates as A minus, it's a weak acid, like phenol for example, OH, it dissociates as O minus and H plus. So the equilibrium constant for this dissociation reaction we could write as Ka, as H plus into A minus divided by AH. We don't write the water because water is constant, it's an aqueous solution if you like, and pKa we define as minus log to the base 10 Ka. Right? If it's a base, we might want to write it like this: B plus water, giving you BH plus and OH minus, and then again you can write the equilibrium constant Kb if you want now. Kb if you want for now, equilibrium constant for the base, you can write as concentration of BH plus, concentration of OH minus divided by B and water. So you can say Kb would be BH plus OH minus divided by the B. So here I am just writing it as equilibrium constant K. Water I am not going to write because it's a aqueous solution, so the water concentration is 55.55 molar. So we define Kb like this, right? And this Kb could be small, and therefore we don't like to write in terms of 10 raised to minus something. So for example, if this K is small, it could be 10 raised to minus 4, minus 5, minus 4.8, things like that. So we don't want to write it like this. We write it as like we do for pH, where we write it as minus log to the base 10 Ka, or we write it as pKb as minus log to the base 10 Kb. And obviously in your undergraduate course you must have seen pKa plus pKb would be the solubility product of water, H plus and OH minus. Solubility product of water, because it's all in the, or ionic product of water. I should not say solubility product, I should say ionic product of water. So for acidic solutes, lower pKa, what does it mean? Does it mean more acidity or less acidity? More or less, which one? And same way, if you take basic solutes, basic solute would be, let's say I take pyridine. Pyridine is a basic solute because it has a lone pair nitrogen. It can accept a proton from water and it will give you NH plus and OH minus, right? Or a tertiary amine, R3N, it would be R3NH4 plus and OH minus, right? Quaternized ammonia. So for basic solutes, higher pKa, does it mean more basicity or less basicity? I want you to think about this. So if you want to imagine two situations, suppose Ka pKa is, let's say 4 or pKa is, let's say 8, then this would mean that Ka would be 10 raised to minus 4 and this would mean Ka would be 10 raised to minus 8. Which is higher, 10 raised to minus 4 or 10 raised to minus 8? Obviously 10 raised to minus 4 is higher, isn't it? Right? So that means this, if pK is 4, K is larger. If K is larger, that would mean that it is more dissociated. The forward reaction is more favored. So lower pKa means more acidity. Do you agree with that? Now look at it the other way around. What does higher pKa mean for a base, for a basic solute? Higher pKa means lower pKb, because pKa plus pKb is equal to 10 raised to minus 14. So if I have higher pKa, it means it will have lower pKb, and therefore lower pKb would mean more basicity. Do you agree with that? Okay, just think about it. If you want, you can go back and revise your undergraduate course, and you can see more examples, and then you can make sure that you really understood what we are talking about here. Okay. Next concept I want to ask is, say for example, benzoic acid has a pKa of 4.2, phenol has pKa of 10, right? So benzoic acid would be like this, COOH. Benzoic acid would dissociate as COO minus and H plus. And phenol, we saw that phenol would be OH, phenolate or phenoxide ion, O minus and H plus. Right? Suppose I make an aqueous solution of benzoic acid, or if I make an aqueous solution of phenol and I keep different pH of the aqueous solution. So are you able to understand what I am asking? So we have an aqueous solution. I have an aqueous solution of benzoic acid and I maintain different pH of this aqueous solution. I can maintain pH of the aqueous solution by adding, let's say, HCl or H2SO4 or HNO3. I can add and I can get whatever pH I want. Suppose I get pH equal to 1 or pH equal to 3 or pH equal to 5 or pH equal to 7 or whatever I want. I can adjust the pH to any value I want. If I have different pH values, what would be the degree of dissociation of benzoic acid or phenol, and at what pH it would be 50% dissociated? It's a basic undergraduate kind of a question. Can you now think and tell me? Can you think and tell me? So what we are trying to say is, suppose this is our, if I want to write our acid like this HA or AH, whatever we want to say, then we say that AH would get dissociated as A minus and H plus. So our Ka is our concentration of H plus, concentration of A minus divided by HA, and this is our Ka. And for, let's say, benzoic acid, so this Ka would now be 10 raised to minus 4.2, isn't it? So if I say pH equal to, let's say, 3, then H plus ion concentration would be 10 raised to minus 3 A minus divided by HA. This would be 10 raised to minus 4.2. So at pH 3, the ratio of A minus to HA is going to be this ratio. Somebody calculate this number, 10 raised to minus 4.2, 10 raised to minus 4.2 divided by 10 raised to minus 3. This would be 0.063. Right? So this ratio would be 10 raised to this ratio of A minus to HA would be 0.063. So if I say, suppose we had started with 1 molar solution of HA, then, and suppose X moles had dissociated, and we suppose you take 1 liter of 1 molar solution and X moles have dissociated, or we say the concentration of the dissociated A minus is X molar, then the numerator would be X, the denominator would be 1 minus X. So X divided by 1 minus X would be 0.063. So X would be 1, X would be 0.063 divided by 1.063. Right? Do you agree with that? This would be 0.059 or 5.9% dissociation. Right? It is not that this ratio is directly the degree of dissociation. The ratio is telling you what is the ratio of those concentrations at equilibrium. I want to know the degree of dissociation. Right? So suppose if I had taken pH 7, then this would be 10 raised to minus 7. and then this number would be 10 raised to minus 4.2 divided by 10 raised to minus 7. This would be 630.9. So this x divided by 1 minus x would be 630.9. Then this would be 630.9 divided by 631.9. And this would be somewhere close to 0.999 something. 99.9% dissociate. Right? 99.9% dissociate. Let me go one second. Going forward. This would be 99.9% dissociate. Do you agree with that? Is that okay with everybody? Is everybody confident, comfortable? Yes, no? Okay, let's go forward. Let's go forward. So here is the answer. I'm just showing you the answer now. Right? If I take different values of pH, let's say pH 2, pH 5, pH 8, pH 12. Now you see, benzoic acid practically beyond pH 4.5 or 5, you have practically all benzoic acid is in the dissociated form. Whereas for phenol, unless you go to a very high pH, it will be practically undissociated. Now, can you think of how to make use of this property to separate benzoic acid from phenol? Can we use this property to separate out benzoic acid and phenol? So what this means is that benzoic acid is a stronger acid as compared to phenol, isn't it? So suppose I have an organic phase. Suppose we have an organic phase containing now benzoic acid, COOH, and let's say phenol. Now if I add an aqueous base, so for example, if I take an aqueous phase with NaOH, NaOH would react with which component first? Benzoic acid first or phenol first? Benzoic acid first or phenol first? The stronger acid is benzoic acid, so it will react with benzoic acid first, isn't it? It will react more strongly with benzoic acid. So suppose I take an aqueous phase now. So now I add the aqueous phase. So imagine that I have added the aqueous phase. I have created a dispersion. I have done liquid-liquid extraction now. I separate the phases. Now I have an aqueous phase which contains this base, but I adjust the amount of the base so that the pH becomes something like 8. Now you see, benzoic acid at this pH would be practically completely dissociated as benzoate ion and H plus ion, isn't it? H plus ion will come into the aqueous phase. Whereas phenol is at this pH, phenol is practically undissociated. So all the NaOH that I have put in will essentially react with the benzoic acid. It will make sodium benzoate, and then sodium benzoate will come in the aqueous phase, and phenol will essentially remain in the organic phase. Because I have limited my amount of NaOH that I have put in, and I have ensured that the pH is not going beyond 8 for the aqueous phase. then in that case I have practically all the benzoic acid coming in the aqueous phase as sodium benzoate, and very little of phenol will come in the aqueous phase. The amount of phenol that would react with NaOH would be decided by, if you add NaOH, it would be decided by this equilibrium, and this equilibrium at pH 8 is practically all of it in the backward direction. That means there is practically no phenolate or phenoxide ion, and therefore sodium phenoxide or sodium phenate would not get extracted into the aqueous phase. So I can maintain a certain amount of pH to make one of the component react and come in the aqueous phase, taking advantage of the dissociation of the weak acids, taking advantage of the difference in the degree of dissociation, in a sense degree of acidity of the phenols, or acidity of phenol with respect to acidity of the benzoic acid. I have extracted from the organic phase into the aqueous phase whichever acid is a stronger acid. Do you agree with that? That is a principle of dissociation extraction. This is the principle of dissociation extraction. Okay, so now this is the principle of dissociation extraction, but mind you, we have to keep in mind one thing, that these are not strong acids, these are weak acids. So we are going to have some small amount of benzoic acid also remaining in the organic phase, and there would be a equilibrium between this. In the aqueous phase it will get dissociated, so I will have, first of all, in the aqueous phase I will have undissociated benzoic acid, and I will have a dissociated benzoic acid. Let me draw this. So I will have this equilibrium, and I will have the equilibrium between CH3COO minus and H plus. This equilibrium in the aqueous phase is our Ka, and this equilibrium between the undissociated benzoic acid in the organic phase and undissociated benzoic acid in the aqueous phase, this equilibrium is our distribution coefficient. Distribution coefficient. There are two equilibria. One equilibria between the organic phase and the aqueous phase for the undissociated form of benzoic acid. Okay. And one equilibria in the aqueous phase for the dissociation of benzoic acid. This equilibrium between the undissociated benzoic acid in the aqueous phase, the benzoate ion and the H plus ion, this equilibrium is governed by Ka, and the distribution of undissociated benzoic acid between the organic phase and the aqueous phase is governed by the distribution coefficient D, dA or Ka, or whatever you wanted to call D. We had called it as D, right? Distribution coefficient as concentration of the benzoic acid undissociated in the organic phase divided by the concentration of benzoic acid undissociated in the aqueous phase. This ratio we had called as the distribution coefficient for benzoic acid. I want you to remember that there are two competing equilibria. One equilibria is between the undissociated benzoic acid in the organic phase and aqueous phase. Undissociated. and the other is the equilibria between the undissociated benzoic acid, the benzoate ion, and H plus ion in the aqueous phase. I want you to remember that these two equilibria exist. Okay. Just to make sure that you have understood that these are two different equilibria, let's do one or two problems. Let's do one or two problems just to make sure that we are able to understand and we are able to calculate all these things. Okay, here is a problem. Right? So many times when you make pharmaceutical compounds, they are either weakly acidic or weakly basic in nature. Okay, so let's just say that there is a API, active pharmaceutical ingredient, made by some fermentation. It is denoted as, let's say, AH in the aqueous phase, and in the aqueous phase AH dissociates as AH in the aqueous phase as A minus and H plus, and dissociation constant is Ka, which you write as H plus A minus divided by AH. Now in one particular case, when AH was extracted into an organic solvent, the overall distribution coefficient D prime was found to be 4.2 and 0.2 at a pH of 4 and 5.5 respectively. Remember, now these are some of the definitions. This distribution coefficient we had called as D, right? But I can also say overall distribution coefficient for benzoic acid, D prime would be the concentration of benzoic acid in the organic phase divided by the concentration of undissociated undissociated benzoic acid in the aqueous phase plus the concentration of benzoate ion in the aqueous phase. Do you agree with that? Because in the aqueous phase, benzoic acid exists not just as benzoic acid, but it exists as benzoate ions as well. So the total equivalence of benzoic acid in the aqueous phase would be the concentration of the undissociated benzoic acid in the aqueous phase and the concentration of the dissociated benzoic acid, which means the benzoate ions. That is the total form. The whole benzoic acid is in two forms in the aqueous phase, the undissociated form as well as the dissociated form. So the total concentration of the benzoic acid equivalent species would be the undissociated form plus the dissociated form plus the undissociated form. So the overall distribution coefficient D prime we can write as concentration in the organic phase. Organic phase, it is not going to dissociate, divided by the undissociated as well as the dissociated. Whereas the only distribution coefficient D is a physical partitioning. This is physical partitioning. This is physical partitioning of the undissociated form, right? Whereas this D prime accounts for partitioning and dissociation. Okay? Do you agree with that? These are how this is how we are going to define the distribution coefficient. So now in the next problem, what we are told is that the overall distribution coefficient D prime is 4.5 at pH of 4 and 0.2 at a pH of 5.5. This is just the definition again, the meaning of the overall distribution coefficient. The overall distribution coefficient D prime is a ratio of concentration of solute in the all forms in organic phase to that in the aqueous phase. In the organic phase, there is only the undissociated form, but in the aqueous phase, there is a dissociated form as well as undissociated form. So that's D prime, overall partitioning or overall distribution coefficient. And just the distribution coefficient D is the ratio of concentration of AH in the organic phase to the concentration of AH in the undissociated form in the aqueous phase. Okay. Assume that this D and Ka is here, they do not change with pH. I want you to calculate the D prime at a pH of 3. D prime at 4.5 is given, D prime at a pH of 4 is 4.5. So what is told is D prime at pH equal to 4 is 4.5 and D prime at pH equal to 2 is 0.2. That is what is told. And I want you to find D prime at pH equal to 3. Sorry, this is not pH 2, pH 5.5. D prime at a pH of 5.5 is 0.2 and D prime at a pH of 4 is 4.5. I want you to find D prime at pH equal to 3. Just give you 5-10 minutes to solve. Okay, so let's just try to see how to solve. This problem is there just so that you get to understand what is the difference between D prime, the overall distribution coefficient, and the physical distribution coefficient, and how keeping different pH is going to allow us to do a partitioning of different compounds. So let's just try to visualize. Okay, what do we have? Suppose this is our aqueous phase. Suppose this is our aqueous phase. Right? What are we told? We have a weak acid present in the aqueous phase. So AH is present in the aqueous phase. Let me make this aqueous phase little bigger so that we can draw these things properly. So in the aqueous phase, we have this AH, but now it is also going to dissociate as A minus and H plus. All right. Are you able to visualize so far? Now, what else do we know? We want to do extraction. Right? It was extracted into an organic solvent. Right? That means we have added the organic solvent. This organic solvent is now going to have AH. In the organic phase, it is not going to dissociate. Do you agree with that? In the organic phase, it will remain as AH. So we have an equilibrium between the AH in the organic phase and the aqueous phase. This is just the physical partitioning. Right? And this AH going to A minus and H plus, there are two competing equilibria. Do you agree with that? So there is a dissociation and there is a partitioning. Partitioning of AH, the undissociated form, because organic phase AH is not going to dissociate. It is only going to be AH. It is only going to be AH. That's why it is just the physical partitioning of AH between the aqueous phase and the organic phase. Right? Now let's write our definitions. Let's write our definitions. What are our definitions? Our definitions of different quantities. So our Ka, what is our Ka? H plus into A minus divided by Ha. Do you agree with that? This is all in the aqueous phase. This is all in the aqueous phase. Do you agree with that? Yes, no, somebody say something. Okay. Now we have d prime, the overall distribution coefficient. D prime, what is our overall distribution coefficient? D prime is the ratio of concentration of solute, in this particular case AH, in all forms in organic phase to that in the aqueous phase. That means this D prime is concentration of AH in the organic phase divided by AH in the organic aqueous phase plus A minus in the aqueous phase, because in the aqueous phase AH exists as AH as well as A minus in all forms to organic phase to that in the aqueous phase. In the organic phase there is no question of A minus. A minus does not exist in the organic phase, right? If you want, we can write this little differently. AH in the organic phase divided by AH in the aqueous phase divided by 1 plus A minus divided by AH in the aqueous phase. Do you agree with this? I have just divided numerator and denominator by AH in the aqueous phase. So this D prime is now, the numerator is just the partition coefficient, just the distribution coefficient, divided by 1 plus, now look at this, A minus divided by AH in the aqueous phase, A minus divided by AH or HA, whatever you like. Let's go. This is not AH, this is AH. This ratio, so A minus divided by AH. This partitioning, if you want, partitioning is only in the aqueous phase, so you might as well write it as AQ, AQ, AQ. Whether we write AQ, AQ, AQ or we don't write AQ, 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 it's all the same. Because it is dissociation is only in the aqueous phase. So this would be Ka divided by H plus. So this would be Ka divided by H plus. You agree? So this would just be D divided by 1 plus Ka. Can I not write Ka as 10 raised to minus pKa and H as 10 raised to minus pH? Do you agree with that? Or this D prime would simply be equal to D divided by 1 plus 10 raised to pH minus pKa. Do you agree with that? Now you see how the distribution coefficient D and the overall distribution coefficient D prime, how they are related to Ka and pH. Now let's look at our case 1. Case 1, what is our case 1? At pH 4, the overall distribution coefficient is 4.5. At pH 4, the overall distribution coefficient is 4.5. That means 4.5 D prime would be equal to D divided by 1 plus 10 raised to 4 minus pKa. At pH of 4, the D prime is 4.5. At pH of 5.5, the D prime is 0.2. And 0.2 would be equal to D divided by 1 plus 10 raised to 5, sorry, not 5, 5.5, 5.5 minus pKa. Do you agree with that? So we have two equations, two unknowns. One unknown is D and the other unknown is pKa or Ka. Can we solve? Solve for D and solve for pKa. These two equations are there, two unknowns. Two unknowns are D and pKa. Solve. Let's just go forward. Everybody would be able to solve, I'm sure. So D, if you solve, I just have the answer. D would be 15.1 and pK would be 3.6. 3.63 almost. And if you want this, it is 15.11 if you like, D. So now what do you want? At pH equal to 3, that's what we want. Oops, let's go. It's going forward. I don't know what. At pH of 3, we want to find out what is the D prime. So pH of 3, so that means D prime would be D, that would be 15.11 divided by 1 plus 10 raised to pH 3 minus 3.63. 3.63. So this D prime would be almost equal to 12.2. You can see for yourself and you can get the answer for yourself. So now what are we trying to say? So distribution, now you see how the overall distribution coefficient is changing. The overall distribution coefficient was 4.5 at a pH of 4. So this was pH equal to 4. This was pH equal to 5.5 and this is pH equal to 3. It's going forward, I don't know why. Do you see? That means at pH 3, this overall D prime is 12.2. More of it is going in the organic phase at pH 3 as compared to, let's say, pH 5.5. D prime is only 0.2. At pH 5.5, more of it will remain in the aqueous phase because D prime is small. At pH 3, more of it will go in the organic phase because D prime is large. Do you see how changing the pH we are able to make AH remain in the aqueous phase or go into the organic phase? Just like we had talked about the first problem, benzoic acid and phenol. So this is the principle of dissociation extraction. We have two equilibria, one equilibria between the undissociated form of the acid or the base, and the second is the dissociation in the aqueous phase. By tailoring the H plus ion concentration, we can keep more of H in the aqueous phase or make more of H go into the organic phase. That's how we are able to manipulate, because the equilibria is governed by the dissociation equilibria here. One equilibria is here and the other equilibria is the partitioning equilibria. Okay. Let's just take one more problem so that we are sure that we have understood all these concepts. Okay, so here is another problem. Let's imagine that there is now the situation is slightly opposite, the reverse. Imagine that paracresol pKa is 10.28, is a weak acid, very weak acid, is dissolved in xylene at a concentration of 1 molar. So 1 liter of organic phase is contacted with 0.5 liters of 0.5 molar aqueous NaOH and equilibrium is allowed to be reached. Okay. Assume that the distribution coefficient of paracresol is 12. Now remember, what is the distribution coefficient mean? Ratio of paracresol in the organic phase undissociated and paracresol undissociated in the aqueous phase. That ratio is 12. Okay, that's what this sentence is telling you. Okay, I want you to calculate what fraction of initial paracresol present in the organic phase gets extracted into the aqueous phase. And second, part B, if paracresol had not dissociated in the aqueous phase and if the aqueous phase did not have any NaOH, what would be the fraction of initial paracresol present in the organic phase would have got extracted? These are the two questions that I want you to think about. I want you to answer. Into this problem, it's just again similar problem, but it is reverse. Earlier it was in the aqueous phase and getting into extracted into the organic phase. Now it is in the organic phase getting extracted into the aqueous phase. And I have given you the initial conditions. I have not given you the pH. I have given you the initial condition of the organic phase and I have given you the initial condition of the aqueous phase. Organic phase initial concentration is 1 molar of paracresol and aqueous phase initial condition is 0.5 molar NaOH and 1 liter of organic phase is contacted with 0.5 liters of the aqueous phase. So now the phase ratios, all those things we have to worry about. So do this problem yourself. We will see solution in some time. Okay, let's just start looking at the solution. Maybe you got the answer, you don't have the answer, doesn't matter. Let's do the part B first. Right? Part B. I'm just going to write what is there initially and allow equilibrium. If I allow equilibrium to take place, and then I'm going to write whatever is there at equilibrium. At equilibrium. Alright, let's do the part B. We are doing the part B first. Part B first. Okay. Part B, let us write what all things we know initially and what all things we know at equilibrium. Let's try to write as many things as possible. Initially, so we have organic phase, 1 liter. We have aqueous phase, 0.5 liters. Okay, and organic phase has any paracresol. Let's just call it as AH. We have been calling things as AH, right? AH. And if I allow equilibrium to take place, now organic phase will be 1 liter, AH will be here, aqueous phase will be 0.5 liter and AH would be here. And what are we saying? For part B, we do not have any NaOH and assume that paracresol is not dissociated in the aqueous phase. That means we are told to ignore the dissociation part. So now it is just the physical equilibrium. So that should be very straightforward. If the physical equilibrium, suppose this AH concentration is, let's call it as X, suppose, then this AH, what would that be? Distribution coefficient is 12. Distribution coefficient is ratio in the organic phase divided by the aqueous phase. So this would be 12x. Do you agree with that? Now our material balance, what has got lost from the organic phase? What has got lost from the organic phase is 1 liter multiplied by 1 molar. Initial concentration was 1 molar. 1 molar minus what is remaining, 12x. This is what has got transferred from the organic phase into the aqueous phase. How much has got transferred into aqueous phase? 0.5 liters into what initially it was, nothing was there, 0. No AH was there, right? So x minus 0 is what has been gained in the organic phase, just material balance. Okay, do you agree with that? So I would get 1 would be equal to 12x plus 0.5x, 12.5x. So x would be, how much would x would be? X would be 0.08. So this x is 0.08, 0.08. This 12x would be 12 times 0.08, 0.96. So do you see? So out of 1 molar, now the concentration remaining is 0.96 molar. Out of the initial 1 mole, 1 liter and 1 molar, so that's 1 mole. Now I have 1 liter and 0.96 molar. So 0.96 moles is left. So how much would have got extracted? 0.04 moles. 0.5 liters of 0.08 concentration. 0.08 is the concentration, 0.5 is the volume. So 0.04 moles have got extracted out of the how much initial? 1 mole initial. That means it is 4% extraction. Do you agree with that? Okay. Let's go to part A now. Let's go to part A. Again, let us draw what is there initially and what is there at equilibrium. Initially, I have organic phase 1 liter. I have AH. Concentration of AH is 1 molar initially. Now I have aqueous phase 0.5 liter. I have NaOH, which is 0.5 molar. So 0.5 moles per liter. This is our initial. Now we are allowing equilibrium to take place. We are allowing equilibrium to take place. We have the organic phase 1 liter. We have AH. We don't know how much it is. We have the aqueous phase. We have the aqueous phase, which is 0.5 liter. In the aqueous phase, we have AH, but this AH is dissociating as A minus and H plus. And in addition, we have NaOH. So that means we have Na plus ions and we have OH minus ions. Do you agree with this? Just try to visualize the physical dissolution, that is the equilibrium between AH in the organic phase and AH in the aqueous phase, undissociated form. Just the physical distribution, partitioning. Now we have AH being dissociated in the aqueous phase, it will give you A minus and H plus ions. In addition, the aqueous phase will contain Na plus ions and OH minus ions. Okay. Let me just write it little bigger so that we are able to visualize the two equilibria. I'm just writing it like this. We have A minus and we have H plus. And in addition, in the organic phase, in the aqueous phase, we have Na plus ions and OH minus ions because we have added NaOH in the aqueous phase. Alright, are you able to visualize? If not, just take your time to visualize. Can we go forward? Are we able to visualize? Okay, so now let's write. Suppose now this is our x. This would be 12x. Let me just write it with another color. Suppose this is x. This would be 12x. Just the physical distribution coefficient is 12. Also, we know that pKa is 10.28. What does that mean? That means H plus into A minus divided by AH is 10 raised to minus, pKa is 10.28, 10 raised to minus 10.28. If you find out what this 10 raised to minus 10.28 is, let's do that. 10 raised to minus 10.28, just to simplify. This is 5.248 into 10 raised to minus 11. 248. You can say 25 if you want. Just make life a little simple. Okay. What is the Na plus concentration here? What is the Na plus concentration in the aqueous phase? Sodium hydroxide is a strong base, so it is going to be completely dissociated. If we assume that Na plus concentration would be 0.5, do you agree? Now, what about electrical neutrality? Solutions have to be electrically neutral. So that means electrical neutrality. That means Na plus ion concentration of aqueous phase, if you write, because only in the aqueous phase we have ions. Organic phase there are no ions. So Na plus ions plus H plus ions, can we say that this is equal to A minus ions and OH minus ions? All the positive ions must exactly balance all the negative ions. Do you agree with that? Yes, no? Now, what can we say about H plus and OH minus? They must also be related by the ionic product of water. Don't you agree? In addition, I must be having, because it's an aqueous solution, H plus into OH minus would be 10 raised to minus 14, ionic product of water. Now imagine what can we say about Na plus ions as compared to H plus ions, and what can we say about A minus ions as compared to OH minus ions? So if you take base which is small in amount as compared to, so say I have 1 mole of AH, whereas I have only 0.25 moles of NaOH. That means base amount of the base is going to be very small. That is going to react with the AH. If it is going to react with AH, the amount of OH minus ions that are left, because these H plus ions and these OH minus ions are going to react, they will react with each other till this condition is established, isn't it? Till the ionic product of water is satisfied. But at least what we can say is lot of the H plus ions would get neutralized by the OH minus ions, or vice versa. Can we not say that Na plus ions would be very, very large as compared to H plus ions? And can we not say that A minus ions would be very large as compared to OH minus ions? Just think about this. Just think about what we are saying. If I am putting 0.5 molar NaOH, the concentration of Na plus ions would be 0.5 molar. Total will be 0.25 moles of Na plus ions. OH minus would be generated in the same amount, but these OH minus are going to react with the dissociated AH, the H plus ions coming from the dissociation of AH, till the ionic product of water is satisfied. H plus into OH minus is 10 raised to minus 14. You see that H plus into OH minus is 10 raised to minus 14, whereas this Na plus is like 0.5. 0.5 molar is what I had put in initially. Na plus ions are not going to go into the organic phase. Na plus ions are not going to disappear as such. So even at equilibrium, the Na plus ion concentration is going to be 0.5 molar. Don't you think this 0.5 is very large as compared to 10 raised to minus 12, 13, 14, 10 raised to minus 10? If that is the case, then I can neglect this in comparison to Na plus. I can neglect the H plus ions concentration in comparison to Na plus ion concentration. I can neglect the OH minus ion concentration as compared to the A minus ion concentration. That means what we are saying is Na plus ion concentration is same as A minus ion concentration is same as 0.5, which means AH will come into the aqueous phase, dissociate till all the Na plus all the OH minus ions which are generated by 0.5 moles of NaOH are neutralized. We are almost going to reach pH equal to 7, near about pH 7. We don't have to have exact pH 7. Even if pH is 8, H plus ion concentration would be 10 raised to minus 8. OH minus ion concentration would be 10 raised to minus 6. Imagine a situation. H plus ion concentration is like 10 raised to minus 8. OH minus is like 10 raised to minus 6. Or even if you reach pH 4, H plus ion concentration would be 10 raised to minus 4. OH minus ion concentration would be 10 raised to minus 10. In any case, it is small as compared to 0.5 molar. Just think about this. Try to visualize what is happening. Okay. If that is the case, now I can write things even more in a more simplified manner. I don't have to worry about this H plus ion anymore. I don't have to worry about this NaOH minus ion anymore because they are very small in amount. They are very small in amount. I can simply say that I can simply say that this A minus would be 0.5 molar. Right? As if in the aqueous phase I have sodium Na, sodium A and AA, Na plus and A minus, the sodium salt of the paracresol. Paracresol, remember what is paracresol? It is OH and CH3. So this is going to dissociate as O minus, CH3 and H plus. So as if I have the sodium salt of this phenolate, chrysolate ion, if you like. We don't call it chrysolate, we don't call it sodium chrysolate, but if you want to call it that way, it's fine. Okay. Now material balance can we do? what is lost from the organic phase? 1 liter into 1 minus 12x. That is what is lost from the organic phase. What has appeared in the aqueous phase? 0.5 liters into, it has appeared as AH and A minus. It appears as AH and A minus. It appears as AH and A minus. So it would be 0.5 into x plus 0.5. Right? So this would be 1 minus 12x would be 0.5x plus 0.25. One minus 12x it would be 0.5x plus 0.2. So this is 12.5x would be 0.75. 1 minus 0.25. X would be equal to how much? 0.75 divided by 12.5. Somebody calculate. 0.06. So now this x would be 0.06. Let us move forward. This 12x would be 12 times that, 0.72. So out of the initial 1 mole, 0.72 moles are remaining in the organic phase. Percent extraction would be 28%. Percent extraction would be 28%. 28% would be extracted, 72% would remain. So couple of things again. If you don't want to make this assumption, right? If you don't want to make this assumption, that's fine, right? You may not want to make this assumption, that's fine. That's okay. Don't make this assumption. You can rework this problem by not making this assumption as well. Let me rub this out. Let's see, there is a faster way to erase. Faster way to erase is only erase all the things. I don't want to erase all the things. I want to erase only this working. If you don't want to make this kind of assumption, it's okay, it's fine, but you will have to still invoke ionic product of water, because this whole of aqueous phase is in the form of whole of aqueous phase has water present in it, isn't it? So we will have to account for the equilibria or ionization or ionic product of aqueous phase, that we still have to account for. Electrical neutrality is going to tell you this. Okay. Electrical neutrality is going to tell you this. Let me just work out. Right. So now let's work out again. This is x. This is 12x. This is no longer 0.5. Okay. H plus into OH minus ion concentration is going to be equal to 10 raised to minus 14 ionic product of water. This is what we will have to invoke. Okay. So now suppose I say this A minus is equal to Y. If A minus is equal to Y, concentration of A minus ion concentration in the aqueous phase is say Y, then what can I say? if A minus is Y, right, these two equations I can rephrase Na plus H plus I can write in terms of OH minus 10 raised to minus 14 divided by OH minus would be equal to A minus plus OH minus, isn't it? Now A minus I want to say is Y. Na plus is going to be 0.5. Okay. Now if A minus is Y, I can use that here, H plus into A minus, that is Y, divided by AH in the aqueous phase, that is X. This would be 5.248 into 10 raised to minus 11. So let me write it the other way around. Let me write this as H plus, and let me write this OH minus as 10 raised to minus 14 divided by H plus. H plus we can write from this. H plus would be 5.248 into 10 raised to minus 11 into X divided by Y, and this would be 10 raised to minus 14 divided by H plus ion concentration. H plus ion concentration would be 5.248 into 10 raised to minus 11 X into Y. So I have a relationship now between X and Y, which is decided by ionic product of water. Now I can write material balance. Again, same material balance will be there. 1 liter into 1 minus 12x would be equal to 0.5 liters into X plus Y. Material balance for AH in the organic phase and AH aqueous phase. What is lost from the organic phase? This is what is lost from the organic phase. This is what has appeared in the aqueous phase. That is for AH. So I have one relationship based on material balance. I have another relationship based on the electrical neutrality. You can solve two equations, two unknowns, X and Y. Solve for X and Y, isn't it? Do you agree with this? Would you be able to solve? Try that. Use Excel, use goal-seek function in Excel to solve, and you will still get very close to 28%. You may not get some 27 point something, because this is a very minor change. You see now this 0.5, how large it is as compared to this term. X and Y are like molar concentrations. So X and Y are of the order of 1. So 5.248 into 10 raised to minus 11 is going to be very small, into X divided by Y is going to be very small as compared to 0.5. Right? So but don't trust, you can just do this yourself. Or if you want, you can write a material balance for OH minus ions. OH minus ions, how much did we have? We had 0.5 molar, 0.5 liters of 0.5 molar. That would be the OH minus ions. And the OH minus ions, now we can come from here. This is your OH minus ions. So we had another relationship in X and Y. Either you do OH minus ion balance. This would be now OH 10 raised to minus 14 divided by Y, of course this is concentration, so I don't have to multiply by this 0.5. Both ways I am only writing the concentration. OH minus ions, well, I think OH minus ions we should not write, because OH minus ions are getting reacted, so let's not write for OH minus ions. It is just this material balance and this ionic product that's going to allow you to find out X and Y. You should not write balance for OH minus, because OH minus ions are reacting. I have 0.5 initially, but I don't have 0.5 moles at the end. Right? They are reacting, so it's not correct to write OH minus ion balance unless I account for reaction. Okay, so that is your homework. Solve this and see whether you get 28% or you don't get 28%. Okay. So if you go back to answers, so part B it was 4%, part B it was 4%, part A it is 28%. So you see how adding a base in the aqueous phase has allowed more of paracresol to be extracted into the aqueous phase. Do you realize? More homework for you could be, think about this 0.5 liter and 0.5 molar. Suppose I make it 0.6 molar, 0.7 molar, 0.8 molar, 0.9 molar, or you keep the molarity the same and change the volume of the aqueous phase. 0.6 liter, 0.7 liter, 0.8 liter, 0.9 liter. Right? And see what happens to this 28%. Do this for yourself. How much would be the part? So now if you want homework, part C, repeat part A for different initial NaOH concentration. So we have taken 0.5 molar. Suppose you take 0.6 molar. Suppose you take 0.7 molar. Suppose you take 0.2 molar. How the percent extraction would change? You see that for yourself. Calculate for yourself. What we are going to do in the next lecture is slightly more advanced version of this. Now in the organic phase, we are going to have two compounds, let's say AH and BH, and we are going to extract with a base. Okay, and then we will see what happens to the separation factor, how much A remains in the organic phase, how much B remains in the organic phase, how much A comes in the aqueous phase, how much B comes in the aqueous phase. Now you will be able to see that depending on their acidity and depending on their distribution coefficient, in this case it was 12. So if you have a distribution coefficient for BH as well, maybe it is 5, maybe it is 25, depending on how the distribution coefficient and depending on their basicity, how more of A or more of B would get extracted into the aqueous phase and the other one would remain in the organic phase. That's how we would be able to do the separation of A and B. That is the principle behind dissociation extraction. Okay, that's what we are going to see in the next class.